In this video we're going to look at rounding. Now we'll start off by looking at the decimal numbers first. So let's say for example we had the number 5.2 and we wanted to round this to the nearest integer. Then we know that the 0.2 is closer to 5, so we would round it down to the value of 5. If we had 5.8, then we know that the 0.8 will take it closer to the value of 6, therefore we would round it up to the value of 6. So I'm sure most people will have seen that before. Now let's say for example we were exactly halfway, that is at 5.5. So the 0.5 is just as close to the value of 5 as it is to 6. So the question is, do we round it up or do we round it down? Now we're going to perform round to nearest even. So let's see exactly how round to nearest even is going to work for this example. So if we had the number 5.5, then what we do is we go to the integer value. If the integer value is an odd number, then we round up. So in this example here, the integer value is a number 5, which is an odd number, therefore we round it up to a value of 6. Now if we had 6.5, you can see that the integer value here is an even number. If we had an even number, then we just round down to that even number, so we get a value of 6. So here's another example. If we had 23.5, you can see that the integer value here is a 3, which is odd. Therefore we round up to the next nearest even, which is 24. If we had 24.5, you can see here that the integer value here is a 4, which is even, so we round down to that nearest even, which is the value 24. So this is quite simple. If the integer value is odd, then we round up to the nearest even. If the integer value is even, then we just round down to that integer value. Now the reason for doing that is if we were to, say for example, always round up, so if we had 5.5 and we always rounded it up to the next integer, or if we had 5.5 and say we always rounded it down to the value of 5, then by continually rounding in the same direction, whenever we get the halfway result, it's going to create a possibility of systemic errors. That is, we continually round in one direction, then we'll continually increasing an error value. So the rounding to nearest even should statistically lead to an even distribution of either rounding up or rounding down, as we expect to be working with numbers that are both even and odd, statistically speaking, say the same number of times. So what do we mean by the values of even and oddness whenever we're talking about binary numbers? Well, you can see here we have the binary number 1001, which is a 9, and this is 1 all zeros, which is an 8, and this is 1101, which is 13. Now you'll notice that the odd values only occur when the least significant bit is a value of 1. So in binary, the least significant bit determines the evenness or oddness. So if the least significant bit is a 0, then the number is even. If the least significant bit is a 1, then the number is odd. So with floating point numbers, what exactly is it we're rounding and why are we rounding it? Now this is best seen by an example. So if we go ahead and open up the spreadsheet in the resources section, so we've got the usual spreadsheet, which is our add and subtract. So if you double click on the add subtract, and we'll put in a couple of numbers. So let's say we put in the number 0.1 and the other, so 567.1, and we'll add on the number, say 7.1. So we can close this for now, And you can see that the x number is bigger than the y number, so we don't have to do any swaps. So we've got our x and our y here. We don't have to swap them. And then we add on the 24th bit. Now we've added on the 24th bit. Now we've got to align the bits. And this is really the point at which we're going to introduce errors. Because we've got two numbers that have come in. Now, as far as we're concerned, these numbers are exact. We've been provided with them from the previous section on some integrated circuit. So when they come in, we make the presumption that they are exact. Well, they are exact. They're the only bit of information we have. But then what we're going to do here with the y value is we're going to take the mantissa and we're going to have to shift the mantissa value to the right, because we have to, before we can add up, we have to make sure the exponents are the same. So we take the exponent of the y and we increase it to the exponent of x, therefore we have to decrease the mantissa. So it's this point here, whenever we decrease this mantissa, that we are going to introduce the possibility of rounding errors. So let's see for this example here, we can see that the exponent value for the x is 136, for the y it's 129. When we subtract one from the other, we get our ex minus ey, which is a value of 7. So we know we're going to shift the y value by 7 places. So we can take the y value here, and you can see the y value goes all the way along to the end, and there's a 1, 1 at the end. And we're going to shift this 7 places to the right, so it gets shifted 1, 2, 3, 4, 5, 6, 7. Now it starts at this point here. So you can see here that what's going to happen is the numbers that we did have here, which are the numbers we got from the input, are going to be shifted out. Now what we could do is we could just shift the entire lot out, and then we could just ignore what fell off the end. So these are the numbers that are going to have fallen off the end. So there's 1, 2, 3, 4, 5, 6, 7 numbers. Now if we just ignore those numbers, then in effect we've lost some information. We've just assumed that the numbers here are always going to be zeros. And then whenever we go ahead and we add these two numbers up, we would just be, in effect, if we ignored these numbers, we would in effect just be rounding down. It would be similar to having a result, say for example, a value of say 5.5, and then just deciding, well, if we get 5.5, we'll just always round down. Now, this is a point in effect then that we're going to have to deal with rounding, because we won't necessarily want to always round down or always round up. We in effect want to round to nearest even. So what we do is we go through the normal addition. The two values are added together, so these are the two 24-bit mantissas. They get added together, and we go through the normalization process, and then at the very bottom here we're going to append on the value for the bits here. Remember, these bits here are generated because of the shift of the y value in order to align the exponents. So we can see here that this 0 here in effect would get shifted down to this 0 here, so it's just been appended. Now the other bits here, we're going to call all the other bits here, we're going to call them, you see the S, so S stands for sticky. So all of the other bits here we're going to call sticky bits. And those are all represented just with this one bit here. And we'll talk about that just in a minute. So we've answered the first questions here. What is it that we want to round? Well, we want to round the final result. And why do we want to round it? Well, we've introduced an alignment shift. And we've introduced that in order to make sure that both the exponents are the same. So we want to make the y exponent bigger to equal the x exponent. But whenever we do that, we have to equivalently make the mantissa smaller, so it's the same number. But when we make the mantissa smaller, we're going to lose information off of the end. So what we want to do is retain that information, and we can use that information in order to correctly round. So now the second part here is, how do we determine whether we are below the halfway point, for example 5.25, or if we are above the halfway point 5.75, or whether we're exactly on the halfway point 5.5 in terms of our binary numbers. So you can see here the numbers I've used are slightly different from the previous page, but that doesn't matter, it just makes it a little bit easier. So let's say, for example, we wrote 5.25 out, so we could write that out as 101, so that's the 5, and then the decimal point, and the 0.25, well, to the right hand side here, the first digit would be the 1 upon 2, and then it would be 1 upon 4, 1 upon 8, 1 upon 16, and so on and so forth. And for example 5.75, again we would have the 5.5 here, and then the 0.75 would be half plus a quarter. And the final one here would be 5.5, it would be the 101, and there would be a 1 here, and in order to ensure that it's exactly 5.5, all of the other values would have to be 0. So you can see here we've got a way of understanding whether we're above, below, or exactly on the halfway point. So if the first value here is a value of 0, then it doesn't matter what we do with the rest of these values, we're always going to have a value that's going to be less than the halfway point, because this number here is going to dominate. So this is going to be, would be a value of a half, but we can see that there is no value of a half here, and none of the other numbers here, when you add them together, is going to give you a number that's going to be greater than a half. So that means that if we've got a 0 in here, then we know that we're going to be below the halfway point. So therefore we're going to round down to the nearest. That is, we're just going to get rid of everything off from the right here. Now another instance here, if we had 5.75, we would have a 1 and a 1. So we know we're at least halfway whenever we've got a 1 here. So if we have a 1 anywhere else than the rest of these, then we know that we're going to be more than 5.5. So therefore we would round up. And we know, in order to check and see whether we're exactly halfway, if we have a 1 in here, and we know that all of the other bits are 0, then we know we're at a tie position, that is at 5.5. So how are we going to use this then in order to work out the correct rounding table? But what we can do is we can call this value here the least significant bit. So this is the first part, if you like, of the decimal value, or in terms of our floating point, it's going to be the mantissa value, the least significant bit of the mantissa value. And then the next bit out is going to be called something called the guard bit. So it's going to be the first bit that's been shifted out. So this is the first bit we've managed to save from the shifting of the y value, that is from the alignment. And then all of the other bits here are going to be called the sticky bits. Now what we do, in order to find out whether we have actually got a tie, we need to make sure that all of these sticky bits are actually zeros. So what we can do is we can put them through an OR gate. So all of the sticky bits here go through an OR gate. If the OR gate comes out low, it means that all of these values are low. If all of these values are low, then we know we're exactly at the halfway point. That is, for example, 5.5. But if any one of these values goes high, then we know that we are above the halfway point. So we would be sitting at, for example, 5.6. Therefore, we would then be in this position here. So if we know the least significant bit here, and we know the guard bit, which is the first bit that has been shifted out, and we know the values of the sticky bits here, then we can work out a truth table. Now, just one thing to note is that the way I've created it here, whenever we OR all of these together, when they all get ORed together, we just get one value coming out, and that value we'll call the round bit. So we could put that as the round bit, but all of these here are the sticky bits, so say S1, S2, and so on and so forth. So we've only got these three values here, so from these three values we're going to generate the truth table for our nearest even rounding, so we'll go and do that on the next page. So here's our truth table that we're going to be using for the round to nearest even. We're going to have the three inputs, so we've got the least significant bit here, we've got the guard bit, and we've got the round bit. And remember, the round bit is just the ORing of all of the sticky bits. We're going to have the output here, so either we add one on to the result, or we don't add one. And you can see I've written an example on the right hand side here which describes each of them. So you can see that if the guard bit is a 0, then we're never going to have a number that's greater than halfway. It's always going to be less than the halfway. So in that case there, we would be rounding the value down. So for example, 5.25 would be rounding down to 5. So that covers these four here. So I'll just note these. So this one here, and also these ones here. So those give the same results. Now the other option here, we could talk through this one here. So for example, if we had a 1 in the guard bit, then that would mean that we're actually halfway. And then if all of the rest of the rounding, all of the rest of the sticky bits are 0, then it means that we're exactly halfway. So if we're exactly halfway, we're going to have a tie. So this is the 5.5 case. So we said that if we have a tie, then what we have to do is look at the least significant bit. If the least significant bit is even, then we just leave it. So in this case, the least significant bit is a 0, which is even. So we don't add 1, we just put the 0 on the output here. So that's going to cover this one here. And also the other option down here is the same thing. We've got a 1 here for the guard bit, but the round bit is a 0, so we're exactly halfway there. So we have to look at the least significant bit. If the least significant bit is a value as an odd number, then we're going to have to make it an even number. So we make it an even number by adding the value of 1, and that will change this to a value of 0. So that's the other tie. So the two ties have been completed. Now the other two that are left are whenever the guard bit is a value of 1 and we don't have all zeros, so we have at least another 1 here, then we're going to be above halfway. So that's for example 5.75, which we would round up to 6. And the same one would occur for this one here. It would be 5.75 rounding up to 6. So this is a truth table that we're going to use in order to generate the correct rounding. So let's go ahead and we'll see how we're going to build that in Logisim in the next video. Thank you for listening. I'll get you on the next video. Goodbye.